surface imperfections in the last class, and we talked about the grain boundaries, talked about the stacking faults, we talked about the twin boundaries, the kind of internal surfaces which we have in the material. However, properties are dependent upon the sizes of each crystallite which is present in the material. Therefore, we define the size of each crystallite, what we call the grain, is also called the grain size, grain diameter or grain size number. We shall define this. There is an international standard for this, and we use that international standard which is used even in communist countries. This standard is called ASTM number, which we give by, let us say, small n. A stands for American, S for Society, T for Testing, M for Materials. That is American Society for Testing and Materials. Please, it's not testing of materials, it's testing and materials. Right? And this standard is what we use. For this, we have to look at the structure of the grains. We prepare the specimen, see it under the microscope. Usually metals and alloys are opaque. And to see these crystallites, we have to prepare the specimen, etch it so that grain boundaries are delineated, and we then measure the number of grains in a given area. And that we use for this a magnification of linear magnification of 100. Linear magnification we write as 100x. So area magnification would be square of this times by 4. And the unit area when this standard was made was 1 square inch. Today we call it 645 millimeter square. Which is the square of 25.4. There are 25.4 millimeters in an inch, and we just square this, it becomes 645 millimeters square. So at 100 linear magnification, when we view the microstructure, we take 645 millimeter square area, and in that area we count the number of grains. Let us say that number of grains turns out to be capital N. When we express this capital N as 2 raised to power small n minus 1, and small n is then the ASTM number. Capital N is the number of grains which were measured in the area 645 millimeter square, measured at 100 linear magnification. It would mean then the area and average area of a grain, because no grains are looking alike. They are space filling polyhedra basically. Some are smaller, some are bigger. So average area of a grain would be let us say A, it is 645 millimeter square multiplied by 10 to the power minus 4 divided by capital N. Because this many grains in this much area, and so average area is area divided by number of grains. And the grain diameter is then defined as under root of A. If I do that, under root of this shall become 0.254, and since that is in millimeter square, so it becomes millimeter, and capital N is 2 to the power n minus 1, So it becomes under root of 2 to the power n minus 1. That's the average grain diameter, and small n is the ASTM number. We can define the grain size either by d or by small n. They are relative. And you will notice that as the grain size number increases, the grain diameter decreases. Is that clear? We will be measuring this in the next laboratory class. We will be doing that. What have I written here? You tell me. It's for you to tell me now. I have defined that I am measuring in a 645 millimeter square the number of grains in that area, and that is at linear magnification of 100. So this is a magnification of 100 linear. I told you the aerial magnification would be square of this. So I have multiplied the 10 to the minus 4 to make it actual millimeters square, right? So this is the actual millimeter square as a number n, because you can't see at that actual size. It's too small. So we magnify it 100 times. 1 millimeter length becomes 100 millimeter. But 1 millimeter square would become 10 to the power 4 millimeter square. Is that clear? That's what it is. Is this clear now? Right. So we finish with the crystal imperfections, and then we can now move on to we shall talk about phase diagrams or equilibrium diagrams. Equilibrium you have already seen in the initial classes when we talked about a bit of kinetics and equilibrium. It is defined by the minimum of the free energy, whether it is a metastable equilibrium or the stable equilibrium, which we call the most stable equilibrium. Free energy is at its minimum. Minimum, what is defined in mathematics, you have seen that the slope there is going to be 0 and the second derivative is going to be positive. So that's what the minimum is, minimum of free energy. This we are referring to the equilibrium. Equilibrium, as I said earlier, can be metastable equilibrium or the stable equilibrium. That's what we are using the materials in their state. Most of them are in the metastable state. In the phase diagram, the word first is a phase, and yesterday also I said that we shall define what is a phase in the next class. First of all, let me talk about classically what is a phase. Classical definition of a phase is, it is something which is chemically homogeneous, it is physically distinct and mechanically separable. Let us first understand the meaning of these one by one. Something that is chemically homogeneous. If you take water which is not polluted, pure water, whether you are in Himalayas or you are in Delhi or you are in South Chennai, if you analyze this water anywhere, it is H2O. Chemical analysis is H2O. And whatever you have beaker, from the beaker you can pour it into a small test tube, or you take bigger bucket, same H2O. Any part of the water you take from the beaker, from any corner, it is H2O. No difference. It's chemically homogeneous everywhere. That's what I mean by chemically homogeneous. What is not chemically homogeneous? Let us see that. If I add some oil in water, shake it well. Try to make it as much possible, homogeneous as possible. Leave it for a while. Well, oil will come floating top. Take from the bottom corner, you take with a small quantity of droplet or something, you analyze it will be H2O, or take from the top it will be oil. But there will be an interface where you can take water molecules as well as in the interface you can take the oil molecules. This is something not homogeneous, it is heterogeneous. There are two different things. In the same container I have two different things. This is not homogeneous. Alright? Now if I go on, let's say talk about water, I add some sugar to it, dissolve sugar in it, add more sugar, keep dissolving. It will keep dissolving for some time, but after that if you add sugar, howsoever you stir, it will not dissolve, it stays in the bottom. If you leave it, don't stir it, it will stay in the bottom. Now there is something dissolved in water. If you take any droplet from anywhere, analyze this, you have certain part of sugar, certain part of water. If you take some quantity from other corner, it will be same amount of sugar, same amount of water. But when you take out the sugar crystal which are still settled in the bottom, it will be 100% sugar, no water there. So therefore, this is not homogeneous, it is a heterogeneous thing. I have sugar crystals as well as syrup, the solution of sugar in water. But sugar dissolved in water, the syrup is homogeneous. Anyway I take, yes, that's what I am trying to arrive at. What is the difference between something homogeneous, something not homogeneous? When I have these salt crystals in the syrup, not dissolved, it is heterogeneous. When everything is dissolved, only the syrup, it is homogeneous. Okay? Physically distinct. I already said that. Syrup is distinct from the crystals of the sugar. So you can say that syrup is one phase and sugar crystals are another phase. In that heterogeneous system, there are two different things. So physically distinct means looks are different. Right? So for example, I give an example of oil and water. You shake it and leave it. After some time, all the oil is on top, all the water is on the bottom. You can distinctly see because colors which you see in oil will be different from what you see in water. Oils are usually less transparent as compared to water. Right? You'll be able to see that. And they are mechanically separable. If I give you syrup and ask you to separate the water from sugar and water from this syrup, you can do it. How? You will boil off, the water will be evaporated, and these vapors can be collected, condensed, you get water, and sugar is left behind. Okay? This is not the mechanical means of separation. This is not the mechanical means of separation. What is mechanical means of separation? You pick something like this and keep it here. Pick another thing here and keep it there. That's mechanical means of separation. But when I have syrup and sugar crystals, you can take a teaspoon, put it in the syrup, take out the crystal has been separated from the syrup. The sugar crystal is settled in the bottom, not dissolved. Similarly, when you have water and oil, you can just make a small hole in the bottom of the test tube. All the water will first flow out, and then when there comes an interface, you seal it back, oil will be left behind. Okay? This is a mechanical means of separation. Mechanical, not any chemical or physical means of separation, it's a mechanical means of separation. So anything which can be separated from another by the mechanical means is a different phase. It looks different from the others, there are different phases. And each one by itself chemically homogeneous. Right? If you look at the definition of the syrup which you look at, or you give another solution of, let's say, alcohol and water, they also dissolve in each other in all proportion. It's mixed. You cannot say alcohol can be seen different from the water. Once they are mixed. Looks at one single phase. Right? So, I can say now like we have a solution is a phase. Solution where the crystals or the molecules of sugar have mixed with the water molecules at the molecular level. That's the syrup. Therefore, I am not able to separate them physically. I have to evaporate all the water to get the sugar back. So, you can see like that in solid state, because we are going to talk about materials which are solids. Solid solutions are there. I talked about substitutional solid solutions and interstitial solid solutions. So, solid solutions are going to be phase. Right? So, therefore, classical definition of a phase is a phase, therefore, is that aggregate of the material wherein the mixing of components occurs at the atomic or molecular level. Now here I have introduced another term which is called component. You have to understand this word component. Various components have mixed at the atomic or the molecular level. The example I gave is sugar syrup. Molecules of H2O form one component and molecules of sugar C12H22O11 that forms another component. Okay? If you look at the elements, there is hydrogen, there is oxygen and there is carbon. There are two elements, but I have only two components. So I must define now what is a component. Components are the constituents like elements, ions or compounds in the system, whatever solid state system I am talking about. The amounts of these material can be varied independent of other constituents in the system, the ones which are present in the material. So in the syrup I have sugar, I have water, I have otherwise elements. If you look at, I have hydrogen, carbon and oxygen. Let's talk of water alone, H2O. Can I change the amount of hydrogen independent of the amount of oxygen in H2O? No. So what I can change is the amount of H2O. So H2O becomes one component. Let's look at the sugar, C12H22O11. Can I change the amount of carbon irrespective of the other elements, hydrogen and oxygen? No. So therefore, sugar and water are the two components, not carbon, hydrogen and oxygen. The amount of which I can change independent of the others which are present in the system. Is that clear? So components are these. Now having defined a phase, where I introduced the word component, and having defined components, I have to look at the equilibrium. To look at the equilibrium, first of all let us try to understand what are the variables in the system. My system has two variables which are called thermodynamic variables, temperature and pressure. And these are two. Pressure can be varied from perfect vacuum to very high pressures to whatever industry you can reach. Could be a few gigapascals. It's possible probably to reach. And then we have, other than the thermodynamic variables, pressure and temperature. Of course, temperature is also absolute value 0 Kelvin and can go up to high temperatures. Maybe in laboratory you can develop up to 3000 Kelvin easily. Then we have talked about the components, the constituents of the system, the composition of the system. Those are called the composition variables. And if there are more than one phase, I have to define the composition of each one of them. That's what is called, that's what I mean, composition variable what I have to define is, let's say I have a system which contains sugar and water. Example, I give the syrup. I say it contains 30% sugar. So 70% would be water. I need to define only one composition, 30% sugar. If I give you a gold ornament, I say it contains 20% copper. So the remaining 80% is gold. So I have to define only one. But if I have three things, like in steel, I have iron, I have carbon, let's say I have manganese. Steels can have more than three. I'll just take an example of three: iron, carbon and manganese. I say it contains 0.2% carbon and it contains 1.8% manganese. Right? Then the amount of iron is defined, 98%. So I have to define one component less in number of variables. That's what I have. Number of components that are there in the system minus 1. This is minus 1. Alright, then now we start writing these things in terms of variables, unknowns, and I define the symbols for them. C I use for number of components. Like I have a gold copper alloy, number of components are 2, gold and copper. C is equal to 2. Sugar syrup, I have sugar and water, 2 components, sugar and water. Number of phases in a system. It can be 1, it can be 2, it can be 3, depends how many phases are there. That's P, I represent by capital P, the number of phases. Number of variables in the system are defined as V. We shall work it out how much it should be, because I already stated what it thermodynamic variables plus compression variables. What we can work out depending on how many phases are present in the system. And E is the number of equilibrium constraints. What is defined by the equilibrium? If two phases are present in equilibrium, meaning thereby is the equilibrium was defined as if you give infinitesimally small perturbation to the system, free energy should not change, it should remain the same. Infinitesimally small. Whereas limit delta x tending to 0 is what? Infinitesimally small. And small is delta x. But once I say delta x tending to 0 means the infinitesimally small disturbance to the system and it doesn't change its free energy, it is in equilibrium. Okay? That's the number of equilibrium conditions or constraints we have to work out. Then we shall see how many degrees of freedom the system has. Means what are the variables which can be changed maintaining the system in equilibrium. Degrees of freedom meaning I can change these variables of the system, still the system is in equilibrium. Okay, that's what we shall see. Alright, let us first of all talk about the equilibrium. Let's say I have the phase 1 here in the system and this is the phase 2 in the system. And there are certain components in this C components in the system. So those C components are present in 1, they are also present in 2. But the relative amounts in 1 are going to be different from the relative amounts in 2 of all the components. That means composition of the phase 1 is not the same as the composition of the phase 2. They are different. But once I have the system, I have certain mass of the system that shall remain the same, but is distributed between phase 1 and phase 2. Alright? Infinitesimally small disturbance will not change my equilibrium. Right? Let us say I have a few components in here, like I have copper, I have nickel, I have silver, I have zinc, I have tin. number of components are present in this system. The smallest disturbance I can give to the system without changing the pressure and temperature, let us say, is I can add or remove one atom of one of the components. Let us say I remove from here one atom out of the ith component. Components will be same. The relative amounts will be different. The whole system is one. Whole system is one. Okay, it's one or two systems. This is one system, but it has two phases. Like oil and water contain is one system. Or sugar, syrup, and the sugar crystals is one system.
So then 30% sugar solution and 50% sugar solution will be different phases.
They are different phases if they are not dissolving in each other. If they dissolve, make it 40% or 45%, then it's one phase. If they separate out, they do not mix. Yes, it is one thing. There are two different phases. That is true. Is it clear? Right. It is possible in solid states things to happen like that too. So I have changed the free energy to phase 1. Right? Let us say this amount of one atom corresponds to the amount equal to delta xi, because ith is the component. I call this one atom as the amount equal to delta xi. If the free energy of the phase 1 changes with the ith component with a certain rate, let us say that rate is free energy of the phase 1 with respect to ith component, keeping the other components same without changing them. It says this, right? And the amount which I have removed from this is the delta xi. This is the rate at which it is changing, and then the total amount which is removed is so this is the change which I have made to the free energy of the phase 1. Now I have removed one atom from the system. Mass of the system has changed. When I am given a system, mass cannot change. So let us put this atom back in phase 2. The same atom is put back. So I have changed the free energy phase 2 also. What is the change I have called the free energy phase 2? The rate at which it changes, let us say that rate is this for the ith component, and the amount is added to it. This is the amount which is added, is the change in the free energy phase 2. This is the infinitesimally small perturbation you are given to the system. You can't make smaller than that. One atom, simply one atom you have removed and put it back into the phase 2. Mass is not changed. So net change in free energy at this state must be 0 if it is in equilibrium. Okay? Let's see what does it give us. The total change in free energy system now is therefore what it is. It is 0. The free energy change, the system which is in equilibrium with small perturbation must be 0. And what does it give us then? Yeah, it gives us the rate of change of free energy of the phase 1 with reference to the ith component is the same as the rate of change of free energy of the phase 2 with reference to the same component. This derivative must be equal to this derivative. Right? So I get the equilibrium constraint from this, and if there are more than two phases, it will go on.
According to this, the net free energy change of the system is zero. Net overall of
Because small, I've given infinitesimal power, small perturbation. Because I'm at the minimum of the free energy, and a small disturbance, it will be free energy remain the same. That is the slope is zero there. Right? Right. This derivative is called the chemical potential of ith component in the system, and we write it as so chemical potential of the ith component in phase 1 is the same as in phase 2, is the same in phase 3, same in phase 4, same in phase 5, and so on and so forth. That's the equilibrium. I have done it for one component. If there are C components, this will be valid for all the C components. Right? So, like that, so let us say you talk about some component which is jth component, delta G1, delta Xj is equal to delta G2, delta Xj equal to delta G3, delta Xj, so on and so forth. The chemical potential of jth component in all the phases will be same. That's the meaning of equilibrium in a system. Alright? Now we shall take care of how many variables do we have and how many equations do we have. So how many number of equilibrium equations do I have? Number of phases. For each number of phases minus 1 for each component. Right? I defined already the components. Let's say I have C components, and for each component I should have P minus 1 equations, where P is the number of phases. Is this clear? Mu I in phase 1 is equal to mu I in phase 2 is equal to mu I in phase 3 is equal to mu I in phase 4, and so on and so forth. Is that clear? If there are two phases only, let us say mu I in phase 1 is equal to mu I in phase 2, how many equations do you have? 1. If there are three phases, mu I in 1 is equal to mu I in 2, mu I in 1 is equal to mu I in 3, mu I in 2 is equal to mu I in 3. How many equations? Only 2. There are only 2 independent equations. Third one is not independent. Third one is a relationship, right? So when I say mu I1 equal to mu I2 equal to mu I3, that means there are only 2 equal to signs. There are 2 equations only. That's why I put P minus 1. Multiplied by C, it becomes a number of equilibrium equations we have. The total number of variables what we have in the system. Each phase shall have how many components? C. How many combustion variables do I need? For one phase I'm talking about. How many combustion variables would I need? C minus 1. If the gold and nickel, I need to define only nickel. Gold is already defined. C minus 1. Right? So, combustion variables would be C minus 1 for each phase, and there are P phases. Plus 2 thermodynamic variables, pressure and temperature. This is the total number of variables. Right? Now I have a situation. This is the kind of situation you have come across in school. You have done it in your discussed here also. If you have set of equations in certain number of variables, you have solved them. If there are 3 equations and 3 variables, you have solved all the 3 uniquely. Right? And you get one solution. There is no degrees of freedom for the system. It's uniquely defined. We call it a system with 0 degrees of freedom. The number of variables is equal to number of equations. However, if you have a system where you have less equations and more variables. Say for example, I give you 3 equations and 5 variables. In 5 variables, 3 equations are independent equations. You can solve the system, you will get large number of solutions. Provided you can choose arbitrarily 2 variables, let us say 1 and 2. 2 variables you have chosen, let's say x1 and x2 you have chosen. x3, x4, x5 you will be able to determine from the set of equations. You can fix the values of x1 and x2. If you fix the value of x1 and x5, you can find out x2, x3, x4 from the equations. So, the 2 variables which you choose, the choice is yours. And so arbitrary. We say the system has 2 degrees of freedom. Okay, and we'll get large number of solutions. Such a situation physically in a material is also possible. But water remains water at 1 atmosphere and water remains water at 1.2 atmospheres. Pressure also doesn't change. Right? So this is possible. What is the next situation is when I have 5 equations and 3 variables on. This situation is not a real situation, it could not be with real variables. This situation could exist for complex systems, but it cannot exist for real systems. But material systems are physically present, they are real systems, they cannot be imaginary. Water is here, water is not there. Because full of water and there is no water there, it's not a situation possible. Such imaginary situations are not possible. Therefore, I have to have systems which are real, and this will not be possible. What will be possible is to have more variables and less equations. Or at the most, number of equations equal to number of variables.
How then it is physically possible that we have 3 equations and 5 variables?
Yeah.
For example, how physical conditions can happen?
So we'll come to that. We'll see the diagrams, we'll show you the variables, and we shall show you the existence of the system, and we'll be changing these variables and all that we'll talk about. And physical examples I will give. So it is possible for me to have more variables and less equations, or variables equal to the equations. But I cannot have number of equations more than the variables. That's not possible. And then we define the degrees of freedom as number of variables minus the number of equations. Right. So let's define the degrees of freedom now. Degrees of freedom, as I said, is number of variables minus the number of equations. Variables I wrote down is P into C minus 1 plus 2 minus the equations I wrote down were, for each component I have P minus 1 equations. You can simplify this. Becomes P into C minus P plus 2 minus P into C again plus C. This P into C cancels with this P into C. I'm left with this C plus 2 minus P. And this is what degrees of freedom F is. We call it the Gibbs phase rule, and we write it like this. Easy to remember. A well-planned family will give you 2 children. So you will not forget it, you will remember it. Okay? So that's how usually I normally can write it like that, but this is the way to remember it. This is Gibbs phase rule that gives us the degrees of freedom in a system with P phases present in a system has C components, and 2 of course are pressure and temperature variables which are there. Right, now you ask me some question. We shall start with single component system today. Let's say we talk about C is equal to 1. Alright, here let me write number of phases in the system. Let me write what are the number of variables in the system, and let us write what is the degrees of freedom in the system. I'll start with one phase. I cannot have a 0 phase. At least one phase would be there in the system. One component system having one phase, and we call your variables. What will be the variables? Variables we have already stated is how many? Since there is one component, C minus 1 becomes 0. So it will be no combustion variable, only one component. Pure gold is pure gold. Okay? Only 2 variables are there, and 2 variables are pressure and temperature. Pressure is one variable, temperature is another variable. How many degrees of freedom do I have in the system? F is equal to C plus 2 minus P. C is 1, 1 plus 2 is 3, is 3 minus P. 3 minus P is 2. I have 2 variables, pressure and temperature. I can change both. That's the degrees of freedom. Water will remain water. Between 0 degrees and 100 degrees, I change the temperature. Water remains water. Below 0 degrees, I can go up to the 0 Kelvin to 273 Kelvin. It's all ice. From 100 degrees centigrade to I go to 1000 degrees centigrade, all steam. I'm changing temperature. I can also change the pressure. Of course, there is going to be a limit of changing the pressure and temperature, beyond which it will not be possible to see that equilibrium is to be seen, and therefore I am able to get this. Right?
Can we simultaneously change pressure and temperature?
Yes, we can. I'll show you the diagrams. We'll come to that. Let's first complete this table, then we shall go to the diagrams. Right. Let's have 2 phases present in the system. Variables I shall still have 2, because P becomes 2, C minus 1 is 0. So that number remains 0, so it remains still 2. That's the same as this. And the degrees of freedom I have in the system now are 3 minus 2, that's 1. To see the 2 phases in equilibrium, I have 1 degree of freedom. Means I can change pressure, I can change temperature, I cannot change both. So I want to see the equilibrium between ice and water. I fix atmosphere, and it happens only at 0 degrees centigrade, nowhere else. And a temperature higher than 0 degrees centigrade, lower than 0 degrees centigrade, at 1 atmosphere, which I fix as 1 degree of freedom, it is not, two of them are not present. They are present only at 0 degrees centigrade. Is this meaning of degree of freedom become clear? Right.
Fixing the pressure, we cannot now change the temperature independently.
Yes, it cannot. It is 0 degrees centigrade when I want to see the two of them together. Alright, let's go to the next one. The 3 phases present in the system. Variables will still be 2, pressure and temperature, and degrees of freedom would become now 0. Both pressure and temperature are fixed when you want to see the 3 phases in equilibrium, in this case ice, water and vapors. And that is slightly different from 1 atmosphere, and temperature is slightly greater than 0 centigrade. Right? And we get the 3 of them present in the system. Alright. So that's the phase rule and how these variables are worked and how these phases give rise to that. I cannot have more than 3 phases in such a system, because degrees of freedom cannot be negative. Maximum it can be 0, minimum it can be 0. Right? So therefore I don't have the 4 phases present in equilibrium. Right, I'll show you the unit diagram of iron. Usually in chemistry we have studied the y-axis they take as the pressure and the x-axis is the temperature. I'll take other way around. X-axis I shall take pressure. And the y-axis we shall take temperature. Why I am doing this is all of the diagrams which I am going to talk, they all will have the y-axis as the temperature. So the unary diagram, or unary means one component system, I am going to see the temperature in this. Right. Well, the pressure values will be varying from, let us say, 0 pressure here. In terms of gigapascal, say 10 or 20 here. Temperature, this one let us say 910 degrees centigrade, and here is 1490 degrees centigrade, and then its melting point is very close by. It may not be to the scale, 1535 degrees centigrade. Here we have, starting from the absolute 0, around 1 atmosphere, we have the BCC form iron, what we call alpha. Then from 910 degrees centigrade, where the transformation occurs, it becomes FCC iron, which we call gamma iron. It remains up to 1490 degrees centigrade or so. Okay, and then again at that temperature, it becomes BCC iron, which we call again the delta iron. So up to the melting point, it remains delta iron. Let's call this delta iron. At the melting point after that, it is all liquid. And at very high pressures, which is beyond 10 gigapascals, and at some temperature below 910 degrees centigrade, it becomes HCP ion, what we call epsilon. Epsilon ion is HCP, alpha ion is BCC, gamma ion is FCC, and delta is also BCC. Now let's look at your table which you had seen earlier. One phase in equilibrium. Okay? Alpha is in equilibrium. It's an area bounded by the boundaries. Epsilon is an area bounded by the boundaries. Delta is an area. Gamma is an area. And liquid is an area. Two variables, both pressure and temperature, can be changed in the area to remain in equilibrium. And we can also see that two-phase equilibrium exists along these lines. Along this line exists equilibrium between gamma and alpha. Along this line exists equilibrium between gamma and epsilon. Yeah, along two-phase equilibrium along the line only between alpha and epsilon. So if I am here, I have alpha and gamma in equilibrium. If I change the pressure, increase the pressure, let us say, where do I go? Gamma phase field. It is no more two-phase equilibrium. If I decrease the temperature from here, I reach into alpha region. So I cannot change any one of the variables. And this was fixed here. Once I have chosen this temperature or this pressure, at this point I have chosen that, I cannot change the other one. I have exercised my 1 degree of freedom. Now come to the triple point. I have no degrees of freedom. Pressure and temperature both are fixed. I have no choice. It's just a point in the whole diagram. This is a line. I could have chosen the temperature here. I could have chosen the temperature there. I have 1 degree of freedom when two phases are in equilibrium. But here, all two are fixed in the three phases. Temperature is fixed and the pressure is also fixed. I cannot change any one of them. Degrees of freedom is 0. Right? I think it answers your question. Right. Okay, we shall start from here in the next class.